um, the several concepts, okay, and we talk about the conjugate prior, and we talk about coin flipping example, and how to use RVs and PyMC3, okay, to create a result, okay, and we have this posterior, okay, and but of course the this interval indicates the 94% HPD, as I said. Okay, normally we use 95, but yeah, this book used 94%. Okay, the reason is because PyMC3, the default is 94% MPD. Okay, and by doing so, okay, it leaves like 3% on, roughly 3% on the left, 3% on the right. Okay, roughly. I mean, I'm not saying, I mean, that's because when you create the HPD, it doesn't guarantee like the left-hand side, right-hand side, leftover will be both 3%. But, you know, it's roughly to be like that. Okay, so just want you to be aware. And they will indicate a mean, okay? Of course, I mean, all this can be changed, okay? You can also find the mode. You can find the 95% PD with a different setting, okay? So, but how do we know, okay, the result is consistent? Okay, the result is consistent. Okay, when I say the result is consistent, I'm talking about the model that you use is correct, or the way you analyzed is correct. Okay, in Bayesian data analysis, okay, we do it through the posterior predictive check. Okay, so you can consider posterior predictive check as like the way to verify, I mean, what you have done so far is correct or not. Okay, so we know the posterior is P probability distribution of the theta on the condition of the data, right? So it is denoted as like this. Okay. And the posterior predictive check is to obtain the P, okay, probability distribution of the y hat on condition of given data. So what is y hat? Y hat is your prediction. Okay, y hat is the prediction from the model. Okay, from the model. Okay, so given the data y, okay, how do you calculate the predicted value? Okay, I mean, to be exact, okay, it is done through the two things. Okay, this one, P of theta on condition of y. This one, I mean, we know, I mean, pretty well. Okay, times P of y hat on condition of theta. Okay, the integration of this over the theta. Okay, these two terms. The first one, obviously, is the posterior distribution, right? Okay. The second one here, you may ask, what is this? This is given the model parameter, okay? We want to find distribution of the data point. Okay, we want to predict the distribution of the data point. So it's like, okay, you get the theta from this probability distribution, and then you use that theta to sample y from your model. That's the result of this one. Okay, so you can treat this thing, okay, like posterior predictive distribution. This is a distribution, by the way. Okay, this is a distribution. It's a probability distribution. In other words, okay, when I say it's a distribution, what I infer is like the integral of this. The integral of this is going to be 1, right? Okay, so what I mean here for this formula is that, okay, conceptually, okay, we approximate this integral as a, it's an iterative 2 steps, okay, as follow, okay. It's an average of conditional prediction over the posterior distribution of theta. So this is this actually indicates an average, okay, average over the posterior distribution of theta. Okay, we want to see the predicted value of the y, the data. Okay, so these 2 steps is actually simple. Okay, very simple. I mean, even simpler than we the past work that we have done. Okay, because we first already have the posterior distribution, right? I mean, remember now we are doing the posterior predictive check. So that's when we already have the posterior distribution. So we just randomly sample a certain value of theta from this posterior distribution. You know, just like a regular sample, okay, you can sample any value from a distribution, right? Okay, for example, from a normal distribution, okay, you can sample a value from that, right? Okay, same thing here. Okay, you can sample a value theta from this posterior distribution. Okay, and then that theta can be used in your model. Remember, what is model? The model is the prior and the likelihood, right? Okay, of course now the prior is no longer that important because you already have the posterior, but the likelihood is still valid. Okay, given the model parameter, okay, you can sample the data from the likelihood. Okay, so you can, we feed the value of theta to the likelihood. Okay, and then we obtain a data point. Okay, again, this is through the sampling process. Okay, you just sample it from the sampling distribution or likelihood, I mean, whatever you call it. Okay, so we just repeatedly, doing these 2 steps. Okay, each iteration, it will give us a value of y hat. Okay, so those are the predictions. Okay, this model gives us. Okay, so through this process, this 2-step process, okay, there are 2 uncertainties. Okay, the first one is the parameters uncertainty. Okay, which is captured, which is from the posterior distribution, because you sample a value from your posterior distribution. So that part has an uncertainty. Okay, the second part is from the likelihood. Okay, so that's you can say it's a model uncertainty. Okay, or likelihood uncertainty. So this process, take into these 2 sources of the uncertainty. Okay. And then, okay, remember through this process, okay, repeating this process, actually, we are able to obtain like y hat, okay, which obviously also contain a number of points or a number of values, okay, and now, okay, the previous y. Remember, the previous y represent the data, right? So this y hat is our prediction. So I'm not saying they are the same, but I'm saying that they should be sort of consistent, right? Sort of consistent. I'm not saying like they are the same, but they should be, similar in certain aspect, right? So you check, you use this, okay? We can use them to criticize the model by comparing the observed data, okay, and the predicted data. So y and y hat, we compare them to see, okay, the differences between these two sets, and this is known as posterior predictive check. Okay. So the goal of the posterior predictive check is to check in statistical term called auto consistency. By the way, you guys, do you know what the meaning? What is the meaning of auto here? If you learn English, long enough, you should know like English word consists of like certain parts, right? Like in Chinese we call it 字首字根字尾, right? The root and maybe like the prefix and the postfix. Okay, so auto is a commonly used like prefix term, prefix for the English vocabulary. Okay, so what is the meaning of this prefix? Huh? Nobody know? Somebody give me like some words that start with auto. No, English. Automatic, right? Automatic. Or maybe like a motorcycle, right? Okay. Or like autonomous, right? Okay. So all these words start from auto, right? So the auto actually implies self. Okay, self. Okay, so for example, when we say like automatic, it means that because matic, okay, the matic part is like a kinetic. Okay, it can do something. Okay, so it can do something by itself. So it's like what we know. Okay, what we understand the meaning of the automatic, or motorcycle. Okay, the motors followed by cycle. Cycle, well, are wheels, right? So the auto means like those wheels can run by itself. Okay, so that's the meaning of autocycle. Okay, so that means like auto is a prefix, English prefix, vocabulary prefix for the self. So here, okay, we are checking the self-consistency. Okay, these two things. Okay, the predicted values, y hat, should be similar. Okay, to your data point. Okay, y in certain similar in certain aspect. Okay, to a certain aspect. Okay, so they should look more or less similar. Okay, if this is not the case, okay, there was some problem during the modeling, okay, or some problem feeding the data to the model because, well, you may have problem collecting the data, right? the data may be biased, okay? Or when you collect the data is not prepared correctly, okay? So that's like the problem in addition to the model, okay? So even in the absence of the mistakes, okay, if you check everything and you don't see any issue, okay, I mean, there may still be differences, okay? We will show you an example, okay, today, later, okay? So trying to understand the mismatch, okay, these differences, okay, could lead us to improve, okay, the model. So we may be able to make the model better, okay, or at least to understand the limitation of the model. Because, you know, remember, model is always a simplification, okay? You can never create a model that captures all the factors, okay? That's pretty much impossible, okay? So there are certain limitations, okay, for the model anyway, okay? So, you know, knowing this issue, okay, of the model, okay, is a very good, variable information. Even if we do not know how to improve the model, okay, by knowing the differences, okay, of the predicted value and the given data, okay, it's still a good, a very variable information, okay. So so we previously we already have this, right? And okay. So we begin our Bayesian journey with a very brief discussion about statistical modeling, probability theory, and the introduction of Bayes' theorem, okay? So this is basically a summary of what we have discussed, okay, in this chapter. This is one of the, one of the important chapters, I mean, from the textbook, okay? So we then use the coin flipping problem, okay? So as an example, okay, to introduce like the basic idea of the Bayesian modeling, okay? We talk about how to model the coin flips, and we also talk about how we can use the Bayesian data analysis to do it. Of course, at the beginning, we start by using like those the grid point approach, okay, to compute the posterior, okay. But later on, we also talk about the conjugate prior, okay, which allowed us to analyze the results that without approximation, okay. We can just do it like analytically, okay. But of course, that means we are restricted to a certain prior, okay. I mean, which is beta distribution, by the way, okay, for the binomial likelihood, okay. Through those examples, okay, we know, okay, the idea of Bayesian statistics, such as like using probability distribution to build models and represent uncertainties. And then we talk about why the priors, okay, should be used, okay. I mean, we shouldn't be afraid of using the prior, okay, and we should put the prior on equal footing with other elements as part of the modeling process, okay. It's just like any other assumptions, okay. Any analysis, any data analysis has assumption, okay. So the prior is just another assumption that we use for in the modeling process, okay. Just like a likelihood or like this type of thing, okay. So we end, okay, by discussing the interpretation and the communication of the result of Bayesian analysis, because like when we have the the posterior distribution, okay, how do we, interpret the result, and how do we make sure, okay, that result is consistent, okay? Later on, we will, have a example that goes through this posterior predictive check, okay? But of course, because that involves that, remember, the two-step sampling process. So it is better to be done by program, okay, which will be the main topic of the next chapter, okay? So to summarize the work that we have discussed, this chapter, we start from a true distribution. Okay, so this is the true distribution, or like a data that you collect. Okay, and then okay, we try to use we don't know. This true distribution is something we don't know. We only get this. This is the data. We don't know the true distribution. We get this data through the sampling. Okay, just like when you flip the coin, you do not know the real value of theta, right? Somebody give you a coin, okay, or even if you get the coin from the government, okay, you still don't know the theta of that coin. You can make assumption. You can say, oh, if I get it from the government, it's more likely to be fair. Okay, so it's maybe close to 0.5, right? Theta is maybe it's close to 0.5, but nobody knows the real value, right? So that's what the true distribution is represented. Okay, we don't know the real value, but we can, through this, we can get certain coin flips. Those are sampled, okay, from this true distribution. Okay, so these are the points, these are the data, and with the data, okay, and by constructing a model, okay, which contains the prior, okay, which may not represent, okay, most likely, okay, may not represent the true distribution. It's your assumption, right? And likelihood and prior and the likelihood, the model, okay, these two elements, okay, and combined with the data, you are able to get the posterior distribution, okay, and from the posterior distribution, okay, this represents the parameter of your model, okay, the distribution of the parameter of your model. And then you can sample, value from this model parameter distribution, and then use the likelihood, okay, to sample your predictions, okay. So those are the predictions that you obtain from the posterior distribution. Okay, and then, okay, in the posterior predictive check, okay, you check the distribution of your posterior your prediction, and the distribution of your sample data to see what we meant by the auto consistency. Okay, so that's what we are doing, okay, for the Bayesian data analysis. This is an iterative process, okay, meaning, okay, when you check if there's an inconsistency or if you find somewhere you can improve the model, you need to do it all over again. Okay? So I think I already explained this slide, so I will skip that. Okay? So remember that the posterior distribution, okay, is a consequence of the model and the data. Okay, in Bayesian analysis, posterior distribution pretty much contains all the information needed, okay, for us, okay. So any analysis, okay, must be done through the posterior distribution and or like the derivatives from the posterior distribution, okay, which is like for example like posterior predictive check is also something derived from the posterior distribution, right? So one way to evaluate our model is by computing posterior predictive distribution with the finite sample we got in the first place. So this is the posterior distribution check. Okay. Notice that posterior distribution is a distribution of the parameters in a model. Okay, and the posterior predictive distribution. These two terms are different. Posterior distribution is a distribution, yes. That's like the distribution of the parameters, model parameters, okay, on condition on the given data, of course, okay, or like observed like the samples. That's pretty much the same as the data, okay. And the posterior predictive distribution is a distribution of the predictive values, predictive samples, okay, which is averaged over the posterior distribution, okay. Why do I say it's average over posterior distribution? It's because, remember this formula, this one, okay, when you multiply a probability distribution and do an integral, okay, that normally means that you are average over certain thing, okay, that's the, what you are average on, okay. So, okay, this posterior predicted distribution is also a distribution. Okay, it's also a distribution. Keep in mind. Okay, so process modeling, model validation. Okay, is of crucial importance. Okay, not because we want to make sure we have the right model. Actually, okay, it is because we know we almost never have the right model. That's very interesting. Okay, we actually never have the right model. Okay, why we never have the right model? Because as I already told you, the model is a simplification of a process. Okay, so no model is able to capture all the considerations, all the factors that affect the result. So, well, that's why, we almost never have the right model, okay? A lot of time, you simplify the process, okay? And the simplification will make your model, okay, slightly incorrect anyway, okay? And which is demonstrated by the differences between the predicted sample and the observed sample. Okay, so we check model to evaluate whether they are useful enough. Okay, in a specific context. Okay, so keep in mind this. Okay, specific context. Okay, after all, everything you analyzed through this model will be used in a certain domain. Either it will be used in the medical domain, it will be used in like insurance domain, it will be used in certain domain. So, when I say useful enough, okay, this term, okay, this model, the results, okay, are really useful or not, okay, is actually, okay, will be determined by, a domain, okay, expert, actually, okay. So, and if not, okay, to gain insight into how to improve them, okay. As I said, we may, improve the model, okay, or something like that, okay. Eventually, okay, there's still differences between the predicted sample and the observed sample, but if the predicted sample already represent enough, aspect, okay, then we accept the model actually, okay. So the last slide, okay, in this chapter, okay, I would like to, talk a little bit about why Bayesian inference can be difficult, okay, because, Bayesian analysis, okay, Bayesian Bayes theorem, okay, Bayes theorem, if you check the literature, it was like invented a long time ago, okay, more than 100 years ago, okay, obviously by a guy named Bayes, okay. If you check out the literature, you will find that actually the Bayes theorem was published before that guy, okay, who is actually a missioner, okay. In the old days, okay, if you want to do mathematics, okay, you can only stay in school or, in the church. Why? Okay. At school, I mean, no question about that. I mean, being a professor, I mean, our job is to do research, right? So you can do mathematics research without any problem, okay? But why I say like, other than school is church, okay? It's because, okay, a lot of pure mathematics research almost has nothing to do with like with real application. At least like when they were invented, okay, at the first place, nobody considered it's their like real world applications. Okay, so in other words, I mean, in some sense, you can say pure mathematics is a game, okay, built on certain assumptions. You derive a lot of stuff, okay, from the assumptions. I mean, you can say it's a mind game, okay, if you want to say that, something like that. That's pretty much, okay, about that. So nobody, okay, I mean, because it's a game, right? So other than like a school, professors, okay, I mean, nobody will pay you, okay, to do like a mind game, right? So if you want to, I mean, be a good mathematician, okay, especially pure mathematics, the second job, the second best job is to work for church, because in church, okay, when you serve the God, okay, other than the regular like jobs, like I mean, most of the time you are free, right? You have your own time, right? I mean, in church, like the missionary, I mean, other than because obviously, I mean, in a Sunday they will be very busy because they are holding certain church, religious events. But other than Sunday, okay, they actually have a lot of personal free time. So I mean, if you look at like a mathematics development in the old days, obviously a lot of work was done by professors. Okay, but there are also a lot of important concept being invented by those people in church. Okay, and the base, okay, is a guy serving a church, and he developed the Bayes theorem, and then he actually he actually didn't think. My guess is he didn't think this result is important because he didn't publish this one. Okay, he just before his death, okay, he had just wrote this idea, okay, in his own notes. But after his death, because remember, he's a guy who is interested in mathematics, right? So he has friends, okay, professors, mathematics professors. So his friends, because he's dead, so his friend, basically sort out things he left, his friend accidentally found the notes, and in the notes, there's the derivation of Bayes' theorem, and the mathematician, knows the importance of this idea. So it's that mathematician who really wrote the paper on the Bayes' theorem, and published that paper, So actually, Bayes' theorem was not published by that guy named Bayes, but by his friend after his death, But this has a very important consequence. But this was happened more than 100 years ago. I think it's like a late 1800, late 1800. So it was invented a long time ago, So you may ask, so if you know it is important, why we don't have Bayes data analysis, in the old days? Remember I told you a statistics field is dominated by frequentists, right? Until a recent 20, 30 years, statistics was dominated by frequentists. Why not Bayesian data analysis? It is because, determining the posterior distribution is difficult. Remember when you do the Bayesian inference, Bayesian analysis, remember, from the prior and the likelihood, you are using the data to derive your posterior, and there's an evidence term, which is actually very difficult to obtain, because we are doing, we are trying to derive. Do we have? This is what we are trying to derive, right? Given the data, we want to find the distribution of your model parameter, right? That's the posterior, right? So this thing is going to be what? Remember? P of D, and this is P of D on theta times P of theta. This is the prior. This is your likelihood. When you have a model, it's not difficult to obtain the likelihood, and the prior is from your assumption, right? So the numerator terms are easy to obtain. The issue is denominator. I keep telling you about that, right? This we call this term evidence, and this evidence, in real world application, it is usually represented by the integral, integral, and this integral, the Bayes rule involve computing the evidence, which is the denominator part, and or marginal likelihood. This is one of the marginal likelihood, obviously. So the integral for the continuous case, is difficult, generally difficult, unless you are using spatial prior, like conjugate prior. Otherwise, it's difficult, Another way to do it is to use the variational approximation, which will not be covered in this class, If you are in mathematics department or statistics department, they may teach you the variation or approximation. But anyway, okay, those are ways to get around with like this integration. Okay, the evidence part. Okay, and we already talked about numerical approximation, right? I mean, basically, we use the grid points. Okay, we can use a grid point to approximate this integral. Okay, so we basically cover a space with grid of points and compute the integral by summing across the points in the grid. Okay, so this is like this can be done, and I have shown you examples. But okay, it will be a problem when the parameter space is large. Okay, especially when the dimension is high. Okay, which is usually the case. Okay, the joint parameter space. Okay, if it involves the combinations of parameter values. Okay, maybe even 10 parameters, 20 parameters. Even if you only sample like 10 points from each dimension, it's going to be huge. Okay, so this issue can be resolved by randomly sampling from the posterior distribution. So this random sampling technique called Markov chain Monte Carlo method, okay, actually was derived like less than 50 years. I think it's like about 30, 40 years ago, okay, by a student named Metropolis and his advisor. Actually, his advisor has more contribution. But anyway, okay, that's the beginning of this, MC method. Okay, so this through this, random sampling, technique. Okay, we are able to, efficiently draw the, enough sample points from this, point space, the parameter space, okay, to obtain our evidence, okay, efficiently. Of course, still through computer, okay, simulation, okay. Otherwise, if you, so basically, okay, the prosperous of Bayesian inference, okay, is caused by two factors. The first one is this MC method gets developed, okay, like just you can say recently because how long the mathematics like history is, okay. So recent 30, 40 years is really a short history, okay, for this method, okay. And the second thing is because the widespread of the personal computers, okay. You don't need a GPU card, okay, to do the Bayesian inference, okay. Of course, like if you are able to do the parallel, processing, okay, it may help. Speed up the Bayesian inference, but it's not necessary. It's not necessary. Okay, just a regular personal computer can do the job pretty well. Okay, this is also one advantage over some more sophisticated approach in deep learning. Okay, because deep learning, if you want to do certain inference, most of the time you need the power of GPU, right? So, but Bayesian data analysis normally do not. Okay, so just want to give you an idea. Okay, why the Bayesian data analysis, become popular so late. Okay, even though the Bayes theorem was invented such a long time ago. Okay, so that's about it for the this chapter, and we'll move on to the next one. One moment. So before I move on to the next chapter, okay, as I said, I mean, this chapter, the next chapter involved like, using the program to solve this Bayesian data analysis, and here. So next chapter, the name of next chapter is called Programming Probabilistically. Okay. Oh, by the way, in the past, probably you have like been more you are more familiar with like deterministic programs. Okay. You don't normally do probabilistic programming, but the Bayesian programming, okay, the Bayesian inference programming is inherently probabilistic. Okay, so just want you to understand. Okay, this is a topic of our next chapter, and I plan to we will today is well, it's almost 15 minutes. So let's take 10 minutes break. But before that, I want to tell you. Okay. We will probably cover like maybe 20, 30 slides today of this chapter, but I plan to assign the second homework, okay, before the next lecture, okay. So please, find some time to check out the second homework before the next week, okay. So. Okay, so let's take 10 minutes break. When we come back, we'll discuss, this chapter.